My name is Professor Spiro Pavlidis, and I'm an assistant professor here in the Department of Electrical and Computer Engineering. My lab is called the Lab for Electronics and Advanced Devices and Systems, or LEADS. The purpose of our lab is to investigate and ultimately develop new electronic devices, namely using new semiconductor materials. We focus on three different application areas principally. The first one would be power electronics or power devices. We also focus on telecommunications and high-frequency electronics. And then the third field that we have as an application area would be sensing, biosensing specifically. We work with different collaborators in medicine, for example, to find new opportunities where a patient or just the general population would benefit from a new biosensor. We are looking at ways to predict injury and the way that injury propagates to the body. And the sensors that we're building with them not only will look at injury propagation and development, but also the efficacy of some of the treatments that they're working on as well. And so we can help them with the development of those treatments. The research that we do is sort of at the intersection between electronic materials, electronic devices, and electronic circuits. The philosophy or the problem that we're trying to solve is how do you link the materials that are emerging to the new circuit using some sort of new device. And I think that's a very tricky balance to solve, but a very interesting one for sure. So we do a lot of experimental work. We leverage a lot of the facilities that we have here at NC State. One example of what we work on are gallium nitride HEMTs. These are high electron mobility transistors. And what these devices can be used for is both power electronics as well as high frequency electronic. We design transistors, we design diodes, and then we work with material scientists to figure out what the best ways are for them to synthesize the material so that it will perform well when we make a device out of it. And then we go down to the clean room, known as the NC State nanofabrication facility here, and we fabricate these devices. We put together here a chemical vapor deposition system for two-dimensional materials specifically. What we look at are things like two-dimensional molybdenum disulfide, and from there we can build transistors and other types of devices. And because we have control over the growth itself, we can look at the direct link between the growth conditions, the way that the material is synthesized, in other words, and the device properties. So I just want to give you a quick peek inside. This system is operated by the students in my group that perform research. It is a system that consists of a quartz tube where we flow different chemicals and then we heat them up, and in that hot environment the chemicals react with each other and then will form a solid layer of semiconducting material on the substrate. And from there we can then remove the material and the sample and then go to the clean rooms at NC State and fabricate the devices. And it's in that type of environment that we can build devices at the nano and micro scale. And so we make these devices, we manufacture them ourselves using these advanced fabrication techniques, and then we bring them back to our lab and we test them electrically, try to understand their performance. And so we use this probe station to probe or individually test different semiconductor devices that we make here at NC State. So if you zoom in here, what you'll notice is that we have a few different key components, such as a microscope to be able to zoom in and look at the devices, and then these cables that run in connect to the probes, little needles effectively that we can position in a very fine way to test each of the devices. What I'll show you over here is an example of the device that's under the microscope at the moment. These are actually a series of different types of devices. So what you can see here are transistors. These are GaN high electron mobility transistors that you would find, for example, in telecommunications or in power electronics nowadays. And then we have a lot of other test structures that we use, like diodes and capacitors, to characterize the materials that we put down. And then we talk to the circuits people and try to see, okay, well, what kinds of improvements would you like to see at the device level so that it can become very useful to you. And I like the idea that I see progress in students. I like the fact that students who come to my lab typically never experience advanced fabrication techniques or advanced characterization techniques. And so they come with some general knowledge from the classroom, but they don't have that hands-on experience, which is very unique. And so by the time they leave my lab, they always have gained some new skill set that they didn't have before, and that ultimately leads to progress in their careers, progress in the ways that they deal with problems, approach problems, define them, and solve them. And so I love seeing that progress in them. But from a research standpoint, what's also really gratifying is because what we do is very applied and very much tied into things that the industry is looking at. We see progress in how our research impacts the world. And so we work on problems that companies are interested in, so we don't just collaborate with federal funding agencies, but we collaborate with companies. And ultimately, a lot of the technologies that we're working on are now in commercial products. It's very gratifying to see that what we're working on is very relevant and that we can basically have an impact. So yeah, I find that to be quite satisfying overall. One of the things that I try to do with the students that come into my lab is give them vertical ownership, if you can call it that, of the project that they're working on. So instead of being responsible for a very small and specific part of their project, students get to see the whole development cycle of a semiconductor device. And so they get experience designing the device, making the device, and testing the device. And so I think students that are curious about that entire development cycle, that want to be engaged in multidisciplinary research where they're working with material scientists, working with electrical and electronic engineers, and working with circuit designers would really enjoy the collaborative environment that we have. If you're interested in getting hands-on experience in an environment that is very multidisciplinary, I think the NC State Leads is a very, very good group for you to look into.